So I love the way that Peter Deere in his book, Revolutionizing the Sciences, opens up his discussion of the scientific revolution, a chapter titled, What Was Worth Knowing in 1500? And so what did an educated individual feel was important? What were the things that they knew to be true, that they could build their future discoveries, their future ideas, their future investigations upon? What was it that an educated person knew to be true at the beginning of the 16th century? But we're going to focus today on Aristotle and Ptolemy, because what comes out of Aristotle and Ptolemy is something known as the Aristotelian Ptolemaic worldview. Ptolemy begins to modify Aristotle's theory a little bit. Ptolemy begins to put certain mathematical concepts to Aristotle's theory. And so Ptolemy was aware of potentially competing theories, we believe, but he accepts Aristotle because it makes more sense from his view, from his senses. It makes more sense to say, yes, the earth is immobile. It is centered. But there's a couple of issues with the math and the fact that the earth is actually centered. See, Ptolemy had to use 3 different types of motion that actually complicate Aristotle's theory to make the math work. But Ptolemy is concerned with the math. So he's building on Aristotle's philosophy and taking certain assumptions with Aristotle's philosophy, but he needs the math to work. And so to solve several problems that had actually arisen between the time of Aristotle and the time of Ptolemy, he developed 3 really important ideas for what we're going to call the Ptolemaic system: eccentric motion, epicycles, and the principle of the equant. Now these can get a little bit complicated for us, but we'll start with epicycles. Epicycles is the fact that the planet is traveling around in a perfect circle around a center point, the center point of which is traveling around a larger perfect circle called a deferent. Now, this would explain why sometimes the planets appear to move backwards. Because according to Aristotle's philosophy, they shouldn't be moving backwards, but they should always be moving in the same direction. And so Ptolemy recognizes this retrograde motion, as numerous people had, as a problem. And so Ptolemy says, okay, now how can I explain this problem of retrograde motion? But I do agree with Aristotle that these circles have to be perfect. The epicycle helps explain that. Now, another interesting point that in some ways is a bit contradictory to Aristotle is the fact that Ptolemy says there is this principle of an eccentric point. In other words, the center of the deferent is not actually the earth. It's this center point. Now, Ptolemy has no actual reason for this. And this is where it gets interesting, because Ptolemy doesn't have the philosophical answers. He tries to develop the philosophical answers, and perhaps in his own mind, he was satisfied with those. When the ancient Muslims found Ptolemy, they found in his mathematical works the greatest mathematical treatise that they had ever seen. And in fact, when they translated it into Arabic and began making comments on it, they called it not syntaxis, which is what he called it, a synthesis, but rather they called it Almagest, the greatest. And so Ptolemy's mathematical works far outshone his philosophical works. And so as we move through the centuries in the Arab libraries and eventually into the Christian libraries and universities, Ptolemy's math stands up strong and his philosophy not so much, because he does recognize that philosophically there is an issue here. So once we get to the universities, the 12th, 13th, and 14th centuries, we have these scholars and these mathematicians who are natural philosophers who are studying the mathematics of Ptolemy and the natural philosophy of Aristotle's physics, and putting them together in this thing that we're calling the medieval synthesis. That's why it's the Aristotelian Ptolemaic model, because it's not either one individually. It's a jamming together and trying to explain both. Third motion that Ptolemy needed was a principle known as the equant. The equant says that the angular velocity was not centered on the earth, nor was it centered on the center point of the deferent, but rather the angular velocity of the movement of a planet was centered on another point that Ptolemy called the equant. So he's introducing another center. And again, philosophically, we still have this why question. Why? Why is the center of the angular velocity of a planet not on the Earth? And why does he need this? Well, he needs it because he has to explain why sometimes a planet moves very quickly and other times the planet moves very slowly. Now, also, I want to keep in mind what it is that we're actually talking about when we say the movement of the planets. If we go outside at night, we can see the fixed stars and that they move in a 24-hour period around the Earth. And so we can see this movement at night. And we can also notice that some of those stars begin to wander, as the Greeks noticed. They called these wandering stars planetes, or planets. And so what we mean by wandering is that the planets will be in one constellation, and we notice that over time, some of these stars, these planetes, these wanderers, are moving from one constellation into another. And over the course of years, we recognize that they eventually end up back in that same place again. So we recognize this circular motion that's taking place of these wandering planets against the fixed backdrop of the fixed stars. So they notice that it's moving from east to west, but sometimes over the course of a few weeks or months, the planets begin to move from west to east amongst the backdrop of these fixed constellations. And so that's the retrograde motion. They also notice that the time between moving from one constellation to another, or retrograde, ends up changing. It's not consistent. And since, according to the philosophy, it would be impossible the speed of ether to change its speed, it must be constant, then he needs to be able to explain this. And the principle of the equant, which is the angular velocity that we can view, is dependent on this equant point, was something that Ptolemy could mathematically illustrate, even if philosophically we can't quite find an answer for it. But again, he did try. So as I said, Ptolemy tried to give philosophical meaning to the motions that he described. However, his mathematical work was so much more influential than his philosophical work, which he called hypothesis on the planets, that ultimately it's Aristotle and Aristotelian physics, which had more philosophical meaning, and Aristotle, who was somewhat separated from the mathematical astronomy, but yet the calculations of Ptolemy seemed to be working as far as they could understand the math. And so as we move centuries later, we have this combination of Aristotle and Ptolemy called the Aristotelian Ptolemaic model. And in addition to this Aristotelian Ptolemaic model, which is both the natural philosophy of Aristotle's physics and the mathematics of Ptolemy, the medieval Christians, like their Muslim forebears who had translated it into Arabic and made comments on it, the Christian scholars in the Latin world, as they rediscover these things, they begin to study them and they begin to incorporate Christian philosophy into the natural philosophy of Aristotle and the mathematics of Ptolemy. And so this medieval synthesis is a synthesis of Ptolemy's math, of Aristotle's philosophy and his physics, and the Christian worldview. Therefore, anytime a problem, an anomaly is observed, it must fit within Ptolemy's paradigm, Aristotle's natural philosophy, and Christian teachings. And all of these, they begin to build on top of each other, creating a pretty sturdy foundation, which would be very difficult to crack, as we see in later centuries. So for example, some of these philosophies that we're talking about would be the fact that the earth being the center of the universe. For a medieval Christian, this makes incredible sense because man is special. God created man and God loves man above all things. And so where would man be in God's universe other than at the center? When it comes to the movement of the planets, of course, the movement of ether is a perfect circle because God is perfect. Therefore, the movements must be perfection. And that's an interesting idea. When we move later on and we see the work of someone like Kepler, a mathematician, we begin to see how he's willing to look at the perfection of God through what he considers mathematical beauty in elliptical orbits, not perfect circles. And if we back up from Kepler to, of course, perhaps the most famous of the scientific revolution, Copernicus. Copernicus is a man who has 1 foot in this medieval world and 1 foot in this early modern world. He's a great example of this early modern mindset because Copernicus is willing to challenge Aristotle. He's willing to challenge some of these, the philosophy of the earth being the center of the universe. But at the same time, he is unwilling to challenge the idea of perfectly circular movements. Because for Copernicus, God is perfect. And therefore, the movements of the planets must be perfect. So he accepts a number of things from the Ptolemaic system, from Aristotelian philosophy. And if you think about it, he's building his definition of perfection on those already preconceived ideas. And he doesn't even necessarily realize that he's doing that. And that's why I think I find the scientific revolution and the overall early modern period such an interesting period.